Hi, hello, and welcome to BK'sTechStack. I am BK. Today, we are going to learn about Introduction to LLM Fine-Tuning.
All right, everyone, let's dive into the world of large language models. We've seen how powerful these models are, but often we need them to excel at very specific tasks. This is where fine-tuning comes in. Think of it like taking a highly educated generalist and giving them specialized training in a particular field. We'll be adapting a pre-trained model to a new, focused job using a curated dataset. This helps the model become more accurate and relevant for our specific needs.
So, what exactly happens during fine-tuning? At its core, it's about customization. We take a model that already understands language broadly and teach it the nuances of a specific task using data that's relevant to that task. This process helps the model better understand the relationship between inputs and outputs in that specific context, leading to more refined predictions. Although it requires effort and a good dataset, the result is a highly efficient and effective model for specialized use cases. You might be wondering, why go through the trouble of fine-tuning? Well, it's essential for several reasons. Primarily, it allows us to make LLMs fit very specific tasks, significantly improving how well they understand and relate to the context. It's also incredibly useful for making an LLM an expert in a particular domain, handling those tricky edge cases, and importantly, keeping sensitive data private and secure. For organizations deploying LLMs, fine-tuning is vital for tailoring them to their exact needs. The LLM fine-tuning process can be broken down into two main phases. The first, and arguably most critical, is data preparation. This is where we ensure we have the right data, cleaned, formatted, and ready for training. Once our data is in shape, we move to the second phase, the fine-tuning itself, where we feed this curated data into our pre-trained LLM to adapt it. Data preparation is fundamental for successful fine-tuning. We need to be mindful of several key aspects. First, selecting data that is truly relevant to the task at hand is paramount. Then, accurate labeling and consistent formatting are crucial. Techniques like data augmentation can help us expand our dataset. Don't forget tagging and descriptions for better context. Finally, employing the right tools and techniques ensures this whole process is efficient and effective.
When we talk about fine-tuning, there are two primary methodologies to consider. First, there's Supervised Fine-Tuning, or SFT. This is where we use labeled data to teach the model specific tasks, focusing on adjusting internal parameters. The second approach is Reinforcement Learning from Human Feedback, or RLHF. This method uses human preferences to gradually guide the model's behavior, making its outputs more aligned with what humans consider good or correct.
Let's delve deeper into supervised fine-tuning. Imagine you're giving the model extra lessons with very specific examples and their correct answers, or labels. This helps it learn the patterns for a particular task more effectively. We carefully adjust the model's internal workings, its parameters, but we often leave the final output layer untouched. This approach leverages the vast knowledge already within the pre-trained model and fine-tunes it for better accuracy on our specific objective.
Now, fine-tuning LLMs can be computationally intensive. This is where parameter-efficient fine-tuning, or PEFT, comes into play. PEFT methods are designed to make the fine-tuning process much more manageable. They achieve this by allowing us to fine-tune only a small subset of the model's parameters rather than the entire model. This significantly reduces the computational resources needed, making fine-tuning more efficient and cost-effective, especially for very large models.
There are several popular techniques within PEFT. LoRA, or low-rank adapters, injects trainable parameters into the model's layers. P-tuning, as the name suggests, focuses on learning a special prompt to guide the model. Prefix tuning adds trainable tensors to specific parts of the model's architecture. Adapters insert new, tunable layers, and AdaLoRA is an extension of LoRA that works efficiently with quantized models. Each method offers a different way to achieve parameter-efficient fine-tuning.
Let's take a closer look at LoRA, or low-rank adapters. The core idea here is to add small, trainable adapter layers, which are low-rank, rather than modifying the entire model. This is brilliant because it significantly reduces GPU memory usage since we don't need to track gradients for all parameters.
the training becomes highly efficient, often using just a tiny fraction of the model's parameters. Importantly, LoRA maintains performance close to full fine-tuning and is perfect for specializing models on limited hardware.
Here's a practical example of how LoRA is implemented using the PEFT library. First, we load our pre-trained model in Tokenizer. Then we define the LoRA config, specifying parameters like the task type, the rank, R, which controls the size of the adapter matrices, and LoRA alpha, a scaling factor. Finally, we use getPeftLotl to apply this configuration, and then we can proceed with training the LoRA adapted model. Notice how concise this is.
Next up, we have P-Tuning, which stands for prompt tuning. Instead of changing the model's actual weights, P-Tuning cleverly learns a small set of soft prompts, essentially continuous embeddings that act like instructions. The main LLM stays frozen, which is great for retaining its base knowledge. This method is incredibly parameter efficient, often using even less than LoRA. It works particularly well for instruction-based tasks, guiding the model effectively. This code illustrates P-Tuning. Similar to LoRA, we start by loading our model and Tokenizer. Then we create a prompt tuning config. Key parameters include the task type and num virtual tokens, which determines the length of our learned soft prompt. We then apply this configuration using getPeftModel and train the model. Notice the num labels equals 2 for sequence classification. P-Tuning adapts the input in a way that helps the model perform the specific task, like classification. Let's shift gears to reinforcement learning from human feedback, or RLHF. This is a powerful technique where human judgment directly shapes the LLM's behavior. It works by first training a reward model that learns to predict which responses humans would prefer. Then, the main LLM, acting as an agent or policy, is trained using reinforcement learning to maximize the rewards predicted by this reward model. It's an iterative process where the model learns over multiple cycles to provide better, more aligned responses. Consider a real-world example, generating news summaries. An LLM might initially produce summaries that are too brief, miss key information, or even contain biases. With RLHF, editors review these summaries, highlighting issues like missing facts or awkward phrasing. This feedback is then translated into reward signals. The LLM uses these signals to adjust its summarization strategy, leading to outputs that are more accurate, concise, and adhere to journalistic standards. Fine-tuning isn't just about the data and the method, it's also about the settings, the hyperparameters. These are parameters that are configured before the training process begins, like the learning rate or how many training cycles, epochs, to run. Finding the right balance or sweet spot for these hyperparameters is crucial. It ensures the model learns effectively without being too slow or overfitting to the training data. There are various ways to tune them, from simple trial and error to sophisticated automated methods. It's important to distinguish fine-tuning from another popular technique, retrieval augmented generation, or RAG. Fine-tuning actually modifies the model's internal parameters to embed domain knowledge. RAG, on the other hand, keeps the model's weights the same but retrieves relevant external information dynamically during generation. This means fine-tuning offers deep integration for specific tasks, but RAG is faster to adapt to new data and requires less retraining. Choosing between them depends on whether you need deep specialization or dynamic, up-to-date information. Once we've fine-tuned our model, how do we know if it's actually any good? Evaluation is a critical step. It's not just about running a few tests. We need a holistic approach. This involves looking back at the fine-tuning process, the hyperparameter choices we made, and then rigorously assessing the model's performance. We use specific metrics tailored to the task. For instance, accuracy for classification or relevance for summarization, to ensure the model performs effectively in its intended domain. Hyperparameter tuning plays a significant role not just in the training but also in the evaluation of our model. While tuning can sometimes lead to substantial gains, it might also result in only marginal improvements on certain metrics. Regardless, the quality of our data, both for training and testing, is absolutely paramount. A high-quality dataset often leads directly to better performance metrics. Remember, this is often an iterative cycle. Tune, train, evaluate, and repeat if necessary. To wrap up our discussion on fine-tuning, let's highlight some key best practices. Thorough data preparation is non-negotiable. Consistency and diversity are vital. Choose the right tools. Libraries like HuggingFace and DeepSpeed are excellent choices. Always monitor for overfitting, particularly with limited data. Efficient hyperparameter tuning is key, and using automated methods can help. Crucially, be aware of and actively mitigate potential biases inherited from pre-trained models. Finally, robust model evaluation using appropriate metrics ensures your model is truly effective.
It's really important to be aware of potential biases when fine-tuning LLMs. Remember, these models are trained on vast amounts of text data from the internet, which can contain inherent biases. These biases, like spurious correlations or underrepresentation of certain groups, can carry over into the fine-tuned model. We need to be mindful of fairness and consider how features are learned during fine-tuning to avoid perpetuating or even amplifying these issues.
To help us implement these fine-tuning strategies, several powerful frameworks and libraries are available. HuggingFace provides both Accelerate for efficient distributed training and the Transformers library, which is a cornerstone for working with LLMs and supports various PEFT methods like LoRA. DeepSpeed is another excellent choice for high-performance distributed training, especially for very large models. And platforms like SuperAnnotate offer end-to-end solutions, including data preparation and evaluation tools.
The HuggingFace Transformers library is incredibly popular, and for good reason. It offers a comprehensive environment specifically designed for working with transformer models, including LLMs. It natively supports many of the parameter-efficient techniques we've discussed, like LoRA. As you can see in this snippet, it makes loading pre-trained models and tokenizers straightforward. The ecosystem around it, with its vast model hub and datasets, greatly simplifies the fine-tuning workflow. When dealing with truly massive LLMs, DeepSpeed becomes an invaluable tool. It's a high-performance computing library specifically designed to handle distributed and model parallel training efficiently. This means it can spread the computational load across multiple GPUs or even multiple machines, making it possible to fine-tune models that would otherwise be too large. It also integrates smoothly with the HuggingFace Transformers library, allowing you to combine the ease of Transformers with the power of DeepSpeed.
Congratulations! You just learned Presentation Topic. Now it's your turn to apply these skills. Drop a comment below and let me know what you're building. If this helped, smash that like button. Subscribe to BK'sTechStack for more weekly tutorials and share this with someone who needs it. Visit www.BK'sTechStack.com for free resources, exclusive tips, and our community. Next video, we're diving deeper. Don't miss it.